Welcome back to AP Pre-Calc. Today's lesson is 1.4, Polynomial Functions and Rates of Change. Let's go ahead and start with a little bit of a review of Algebra 2. Remember, back in Algebra 2, we dealt with polynomial functions, and this was the really fancy, mathy way to write it out. It's a bunch of just nonsense, really. It's just what you should do is you should start with your first term being the biggest exponent. We would call that the degree, and then go down by one from there, skipping if you didn't have one, okay? So let's go ahead and answer these questions. The leading term in this case would be the a sub n x to the nth. And remember, this n down here doesn't have any value. It just tells you where it is in the list. But the n up here is an exponent, so that definitely has some value. The degree would be the n, and the leading coefficient would be a sub n. Pretty simple. Hopefully you remember that. So the first thing you got to make sure is that everything is written in order. That's usually it'll be written like that, but if they're trying to trick you or something, they might change the order up. So the first one, a, is written in order. The leading coefficient is 3, and the degree is 4. The second one is not written in order. They kind of move things around. And remember, the minus sign is really a negative in front of that 7. So if we rewrote that, we would start at negative 7x to the third. So the leading coefficient is negative 7. The degree is 3. And last but not least, we don't even have an x. We could put an x there if we wanted to. We could put x to the 0 like that. But you don't have to. We call that a constant coefficient, so that would be a 4. And I guess if you want to put the degree, it would be 0, because you have to have something. All right. Okay, I mentioned earlier in one of the lessons that when your function is increasing and then it goes to decreasing, or it's decreasing and it starts increasing, those points are kind of important to us in upper level math, and we call those maximums and minimums, okay? There are two types of extrema that we deal with, and that would be a relative extrema, local, relative meaning in that little section of the graph, and absolute extrema, meaning throughout the whole graph, from the lowest domain to the highest part of the domain, the highest or lowest. Notice in our two boxes here it says extrema. That is just a plural, meaning there could be more than one. Okay, so we have relative extrema, which are the local pieces. If you wanted to, you could say, like this piece right here, that's a high piece, right? So in this little section, that would be a local maximum. But over here in this section, from like 2 to 4, this would be a local maximum, while this point down here would be a local minimum, or a relative max, relative max, relative minimum, meaning relative to where we are in the graph, what kind of point do we have going on there? So it's asking me some questions down here on the first one, relative extrema. What are our local mins? Well, we definitely have one here. And the weird one is this guy over here. Because it is a closed endpoint there, that is also considered a minimum. So we have one at 0, and we have one at negative 4. Don't put parentheses around that. We don't want to make it look like an ordered pair. We are just giving the x values, the domain values where this happens. And then for the maximums, we have them here. So that would be at negative 2 and 3. And you might be asking why this one isn't one of those. It's because it has an arrow. It goes down without bounds. It goes down to negative infinity. And negative infinity cannot be a maximum or a minimum. Same with infinity. All right, let's look over here at absolute extrema. That means looking at the whole graph from left to right. What is the highest it goes? That would be a maximum. What is the lowest it goes? That would be a minimum. And look what it's asking. It's asking for the maximum and where is it happening. So when I ask you for a maximum or a minimum, I'm talking about the height. That's the y value. If I ask you where that is happening, that's an x value. So there we could give an ordered pair. So looking at this from -4 to positive infinity, what is the highest this graph goes? And it goes up to 2, right? Where did that 2 happen? Well, it happened at 3. What about the absolute minimum? Now, a lot of kids will go, well, we're looking at the graph. That looks like it's the lowest point. But remember, this guy goes down forever. This one does not have one. There is not an absolute minimum. So we could put not available, we could put none, whatever you wanted to put, okay? Go ahead and pause the video, see if you can answer these questions, and then start it back up, and I'll have the answers there. All right, let's quickly go over the answers. Relative minimum, it goes down on both sides to negative infinity, so there is none. The highest it goes is 1, so this is a relative maximum and a global maximum, actually. All right, let's keep going. The absolute minimum, well, we never had one, so we put none there again. And the absolute maximum was 3. The value was 3, and it happened at 1. All right, so we have a little bit different graph here, kind of like the one we saw before. I'm going to go ahead and mark the key points that we want to look at. That guy, that guy, that guy, and we got to pay attention to him too, okay? So go ahead and pause the video, answer these questions. I'll fill it out and we'll check them in a minute. All right, check your answers. All right, so relative minimum, what's the lowest we go? Well, we got a low point here, but not over here because that goes to infinity. So we got 1 relative, like relative to this part of the graph, that's the low part, all right? Relative maximum, well, we got a high point over here, we got a high point over here at -4 and 3. Absolute max, so we got to look at, absolute min, we got to look at the whole graph. Well, the whole graph goes down to a negative infinity, so we do not have an absolute minimum. And the absolute maximum, the whole graph, this piece is higher than this piece, so our maximum value is 2, and it happened at 3. Go ahead and pause one more time and see if you can answer this, and then I'll put the answers on there. Okay, so there are the answers. We didn't have any arrows this time, so all of those points are going to be one of the 2. I hope you got them right. All right, just a couple of fun facts about polynomials. Between 2 real zeros of a polynomial, there must be at least one relative max or relative min. Has to. Look down here on my graph. The only way I can get from this 0 back to this 0 is to turn around. So I'm going up, and I'm like, oh no, I got to get back down to the x-axis, so I have to turn around. That would be a relative max. And the only way to get back to this 0 is to turn back around, because I was going down, then I have to go back up. All right? So if I cross the x-axis 2 times in 2 different places, in between those 2 zeros, there has to be either a relative max or a relative min. Also, if your polynomial is even, you have to have an absolute max or an absolute min. Okay? So, for example, if I have this graph right here, my point down here at the bottom, that's the lowest point for the whole graph. So that is an absolute. Okay? So we have another vocab word here, and it's a points of inflection, okay? These are words that you're going to have to remember if you're moving on in math. You're going to have to remember them for this class, but you're going to see them a lot in your calculus classes, and if you go into a STEM class, you're going to see these a lot, right? So if you remember, when we're going from decreasing to increasing for the values, the heights, okay, not the slopes. If I'm going from increasing to decreasing, that's where we have a relative max or a relative min. But if I am talking about the slopes, the rates of change, if I'm going from a negative slope and then I turn into a positive slope. So I'm going to draw some arrows or some slope lines on the purple line down here. Give me a second. Look at those slopes. They're pretty steep negative for the first one. The second one is a little less steep. The next one is a little bit less steep. So I am actually increasing my slope. It's getting bigger. But then all of a sudden, if you look at the blue lines, the blue slopes, you'll see that they start out kind of flattish and then they start getting steeper in the negative. So now they're actually decreasing. So I went from increasing slope to a decreasing slope, and that is a point of inflection. I went from being concave up because I was increasing my slope to concave down because I was decreasing my slope. So that's what point of inflection means. Your rate of change has gone from either increasing to decreasing or from decreasing to increasing. Your graph went from concave up to concave down or concave down to concave up. All right, here we have an even degree function because both ends are pointing up, so I know that it has to be an even degree. There are a lot of things going on in here. We have some low points, we have some high points, at least relatively. And since I have a low point and a high point somewhere in there, I have to have a point of inflection. There's a whole bunch of things going on. So let's see what it's asking. It says, for any values of x where g has an inflection point. So if I have a relative min, and then I move over where there's a relative max, somewhere in there, there has to be a point of inflection. I had to turn from going concave up to concave down. All right, my slopes went from increasing to decreasing. And to be honest, we usually can't just look at a graph and say, oh, it's at this point and this point. It takes a little bit of work with calculus, but because we're not in calculus, we're going to just kind of guesstimate where it is. And if I had to guess, I would say somewhere in there. So I would say there's a point of inflection at -1. Remember I said at -1, and a point of inflection at 1. Remember, your x value is a where, your y value is a what, and they want to know where. Okay, so looking at this at part B, the last part of our notes, for each of the following intervals, determine if the rate of change is increasing or decreasing. So basically, we're trying to see if our slope is getting bigger or getting smaller. So from 3 to 4, so from here to here, what is going on? I believe that would be increasing, right? What about from -4 to -3? Remember, we would read left to right. The value of my graph, the f, or the g in this case, is decreasing, like the height is getting smaller, but our slopes are also, oh wait, no, our slopes are actually increasing. Wow, wait a minute. You mean that the value of the height can decrease and the slope could still be increasing? Yeah, it's a little crazy like that, right? And you can look at it and say, oh, that's starting a curve that would be curved up. If that's concave up, it has to be increasing. All right, let's look at the next interval from -1 to 1. All right. That whole area, that's where our points of inflection are. In between those 2 points of inflection, the thing is concave down the whole time, so that must be a decreasing slope. And if you drew the slopes in there, you would see that it is decreasing. And then last but not least, from 1 to 2, you can see that at that point of inflection, we changed. We were decreasing from -1 to 1, and then at 1, we started increasing again. All right, and that is the end of this lesson.